In this video, we'll be looking at differential equations with Euler's methods and logistics, and the different kind of problems you'll come across and what they'll ask you to do for these different topics. So let's get right into it. First off, we have Euler's method, and the main ideas that Euler's method problems will ask of you to do is it'll ask you to giving a starting point, initial condition, and the first order differential equation, or any order differential equation, find a specified point in a specified amount of steps, or you could it just wants you to find it, and be able to find the error of a Euler series. So let's get into our first problem right here that demonstrates that giving a starting point, initial condition, and first order differential equation, find the specified point in a specified amount of steps. So the problem that we are going to be reading is approximate f of 1.3 and 3 equals steps, given the initial condition f of 1 equals -3, that the particular solution f of x satisfies the differential equation of dy over dx equals 2x minus 4y. So what does this want us to do? Basically, it wants us to, in 3 different steps, it wants us to find f of 1.3 with an initial condition of f of 1 equals -3. And to do this, you can do it in 2 ways, really. You could do it this simple way, which is shown right here, and it doesn't involve a long chain of point-slope formulas, as you can see. And to do this, what you want to do is you want to find the change x as the x plus the change of x, and y equals y plus the change of y. And to do this, for the initial, since the initial condition is 1, -3, for x, for the first step, it would just be 1 and -3. And this is kind of our 0th step right along here. So what we'd want to do is dy over dx equals 2x minus 4y. And what we'll do is we'll just plug in for x and y, our points that we get for x and y right here. And this is still our 0th step to be noted. So 2 of 1 minus 4 of 3 equals 14. And then what we're going to want to do is that each step is going to basically equal this dy over dx. So since we're taking 3 steps to get from 1.3 to 1 to 1.3, our steps will be at a size of 0.1. So we will take the change of x, which is found right here, dy over dx, and then we'll multiply it by the change in our x right here, which is 0.1. because 0.1 is our steps, and we will get 1.4. So then, to move on to our second line right here, or our first of finding steps, we'll want 1 plus 0.1 equals 1.1, which will give us our x for our first step, and then we will find our y, which is -3 plus 1.4, and if you notice that this point corresponds to this point right here, and this point is our step, and it's just stepping up along all these x's right here, but our y is changing because this is the short method. It is based on the slope method. It's just the slope method formulas. So what we'll do is we'll just go up right here to 1.1 times -4, 1.6, and we get the 1.6 from the y right here, and that finds our slope for our new line, because the Euler's method is basically just as I said before, it's just a chain of point-slope formulas. So then what we'll do is we'll just keep going on and completing this table until we get to our x equals 1.3 mark right down here. And then we'll plug in our y from our previous 0.536 to our 0.74. which can be found right here in our previous one, and we'll get an answer of -0.204. So this one is simple in that you're just finding the chain of point-slope formulas. Okay, let's go on to our next problem, and our next problem will be to find the error of a Euler series, and we'll be focusing on part B mainly, as we already learned how to do part A before. So a curve that satisfies the differential equation dy over dx equals x plus 2 and passes through the point of 0 and 3. Approximate f of 1.5 using 3 equal steps. So you will be taking 0.5 increments is we want 3, and we're getting from 1 to 1.0 to 1.5. And part B, which we're really going to be focusing on, is if the error of the Euler's method is the difference between the approximate and the exact values of y equals 1, solve the differential equation dy dx equals x plus 2 with the initial condition y equals 3, y of 0 equals 3, and find the error. So what this is wanting us to do is, like before, in this problem right here, it is wanting us to find, given initial conditions and dy over dx function, it wants us to find f of 1.5. So what we do is, in this one, we can be seeing using the chain of point slope formulas instead of using the simpler, sometimes more complex, simpler version. We're using the chain of point slope formulas, so x is 0, y is 0, 0, 3, and then plus 0.5 as our step, 3 plus 0 plus 2 times 0.5, which equals 4, and we just go on until we get our answer of 6.75. So what we want to do is, this is 6.75 is our Euler's approximated answer. So in order to get the error of the Euler's methods between the approximate, which is the Euler's method, versus the exact value, what we'll want to do is we'll want to take the derivative of, or the antiderivative, sorry, of dy over dx equals x plus 2, and then we want to find, simply just plug in f of 1.5 in order to get the exact value, the actual exact value of f of 1.5 instead of the Euler's approximation. So we go about doing this, taking the derivative of x plus 2, and then we get x squared over 2 plus 2x plus c, and we can find the important part is c. We have to find the c. And in order to find the c, since we were given an initial condition, it is simple, and we find the c equals 3. We plug this in, and then we plug in, for x equals 2, 1.5, and we find that when x equals 1.3, that this is our Euler's approximate, that this is our actual answer. So what we do is you find the actual value of the point, and you must derive the formula that is given to it, so that it is in the form of the given the position, plug in the x value for the value that you're supposed to in the formula that you just derived. So once we get this actual value and we subtract it, what we do is we get our Euler's approximation and subtract it, and we find that the value that the error is 1.3. So let's go into our next section, logistics. And in logistics, we'll break this into two parts, part 1 and part 2, because there's quite a lot of things that we need to know for logistics in order to solve logistics problems. What we want to do is we want to be able to find a specific data value of the logistic equation given information, initial information. We want to be able to tell when the equation is growing the fastest and at what value the equation is approaching. Be able to find the rate at which the function changes at a certain, and be able to find the rate at which a function changes at a certain point. So let's go into a problem that analyzes this. So this problem is making use of all three of the points that we would need to be able to be aware of to be able to solve logistics equation and what its logistics problems. And the question is asking is the population of a large island in 2000 can be modeled by the following logistic equation. P of t equals 1367.66 over 1 plus 24.33 e to the negative 0.516t, where p is the population and t of years after 1900, with t0 corresponding to 2000. So we need to find the predicted population of the island in 2050. In what year the island's population was growing the fastest. And for part C, it wants us to use a calculator to find how fast the population was growing in 2062. So let's go into part A, find the predicted population in 2050. So because the equation is already given to us in the P of t equals k over 1 plus a to the e minus small k to the t, we know that this is the standard position formula for the logistics equation. So, and if we plug in a value t of time, it'll give us a value of what the population is. So we simply just plug in, since we want to find p of 50, we just plug in 50 for t, since t of 0 corresponds to 2,000. Once we plug this in, we get 48,096.4 people, and we'll round down to 48,096 people. Next, let's go on to part B. In what years was the island's population growing the fastest? So by the nature of a logistic function, we know that the population is growing the fastest when the function is equal to the carrying capacity divided by 2. And the carrying capacity in this equation is given to us by K. Right here on the top, 1367.66. It's the big K, not the small k. The small k will give us the rate at which it's growing. And we will just take K, I'm sorry here, not an A. Just disregard the A. It'll be K over 2. And in this case, 1367.66 over 2, or 6883.83 is when the population is at 68,383 population, the function will be growing the fastest. And now that we know this, we can simply just set 68,383 equal to our equation that is given us and use algebra to solve for t, as shown right here. And we will see that at natural log of 1 over 24.33 is when the population is growing the fastest. So for our last section, it wants us to use a calculator to find the population when the population was changing, the rate at which it was changing in 2062. So by rate, we know that it means the first derivative, because the first derivative will give us the rate at which something changes. So what we can do is we can just plug this into our calculator and find the first derivative of it for 2062, and 62 will equal t, and we'll get 1764.26. Or what we can also do is knowing the laws or whatever for logistic equations, we know that dy over dt equals r of n minus 1 over k n2. So what we can do is we can just plug in all of our values that we know for our equation right here. So we'll see that we have an r, and we will just plug in -0.0516 for our r. And then we will plug in our carrying capacity K. And then for our n's, we will plug in 62. And this will also give us how fast the population was growing in 2062, or rate at which the population is changing in 2062. So here is our second point, our second part of logistics, and this is being able to switch between and derive the different logistic functions, i.e. the position first order differential functions, as we saw right here, this being the first order differential, and this one right here, p of t, being the position function. But some problems will not always be given to us in these p of t and perfect dy over dt forms. Instead, they'll be given to us in problems like number 6 on our worksheet, where a certain student comes down with a long-lasting and contagious sickness. The sickness is transmitted quickly among the student's classmates, and the number of the infected classmates grows, and represented by the logistic equation dp over dt equals 0.4p minus 0.004p squared, where t is measured in weeks and t is greater than or equal to 0. And it wants us to find p of 0 equals 5 and finds the limit as it approaches infinity. And in this, what we need to do is the function is growing fastest based on this, which tells us about the carrying capacity rate and change at a certain